Hello students, myself Nimesh Prabhakar. Welcome to Antenna and Propagation lecture series. So in last lecture, we start the analysis of the oscillating dipole. So in that lecture, we discuss about the what is the oscillating dipole, how it radiates its energy, that means electric power, electric field and magnetic field, and we start the analysis of the oscillating dipole. That means we have find the magnetic field component and electric field component. Now in this lecture we continue that portion, that means oscillating electric dipole part 2. So in this lecture we discussed how the power radiated by the current element in the oscillating dipole. From the last equation, that means in the last lecture we have discussed electric field E has component ER and E theta, while magnetic field has only one component H phi, that we have discussed in the last lecture. So the electric field has two components, ER and E theta, and magnetic field has only one component H phi. Then we write the total E and H as, that means electric and magnetic field as E is equals to ER AR plus E theta A theta. And for the magnetic, we can write the H is equals to H phi A phi. Because the electric field has two components, so we have write the ER and A theta, and magnetic field has only one component, is the phi direction. So we have write the H phi A phi. The complex Poynting vector is given by, so by using the Poynting vector equation, we can write that W is equals to 1 by 2 E cross H. That means E bar cross H bar star. So now we substitute the value of the E and H in this equation. So we get the 1 by 2 ER AR plus E theta A theta, and to multiply by the H phi A phi. So when we solve this equation, so we get 1 by 2 E theta H phi AR minus ER H phi A theta. So this is, when we solve this equation, we get this. Now the complex Poynting vector in general is given by W is equals to WR AR plus W theta A theta plus W phi A phi. So comparing the equation number 1 and equation number 2. So we get WR is equals to 1 by 2 E theta H phi, same as W theta is equals to minus 1 by 2 ER H phi star, and for W phi is equals to 0. So when we compare the equation number 1 and equation number 2, we get the value of the WR, W theta and W phi. Each component of W can now be obtained separately. So we can obtain the WR first. So we have WR is equals to 1 by 2 E theta H phi, and we have the value for the H phi. So when we substitute the value of H phi and E theta in the WR equation, so we get this whole equation. That means 1 by 2 I0L 4 pi r sin theta eta jk 1 plus 1 upon jkr 1 upon the jkr square e raised to minus jkr. This is the value of the E theta, into multiplied by H phi, that is I0L upon 4 pi r sin theta jk 1 minus 1 upon jkr e raised to minus jk. Now we solve this equation. So we get 1 by 2 I0L 4 pi r whole square sin theta into sin theta, so we get the sin square theta eta, and jk into jk, so jk square. And when we multiply these two, so we get the 1 plus 1 upon jkr plus 1 upon jkr square minus 1 upon jkr minus 1 upon jkr square minus 1 upon jkr cube. Now we solve this equation. So we get 1 by 2 I0L upon 4 pi r square sin square theta, theta is same, and jk square. And when we solve this square bracket portion, so we get 1 minus 1 upon jkr cube. Now, so we have the equation WR is equals to minus I0 square L square 32 pi square R square sin square theta eta 2 pi upon lambda 1 minus 1 upon JKR KR cube. So when we solve this equation, so we can write this equation as theta by 8 I0 L upon lambda sin square theta R square 1 minus J upon KR cube. The other component W is obtained by, that means here we have solved the first component, which is WR. Now we solve the W theta. So W theta is nothing but the minus 1 by 2 ER H phi. And when we put the value of the ER and H phi, so the ER value is the minus 1 by 2 I0 L 2 pi R square cos theta 1 plus 1 upon JKR is to minus JKR. And H phi value is the I0 L upon 4 pi R sin theta JK 1 minus 1 upon JKR is to minus JKR. So now we solve this equation. So we get W theta is equals to J eta K I0 L square 16 pi square R cube cos theta sin theta 1 plus 1 upon KR square. So this is the value for the W theta. The complex power moving in the radial direction is obtained by integrating W over a closed surface of radius R. So we can write the equation for the P, that means the power is equals to W integration W dot ds. This is the spherical integration. So we can write the 0 to 2 pi and 0 to pi WR AR plus W theta A theta R square sin theta d phi AR. So now here the AR into AR is equals to 1 and AR into A theta, that means this is the R and theta, that's why this is 0. So we get only the WR R square sin theta d phi. Using the value of WR from the equation number 4. So we have the value of the WR. So now we substitute the value of the WR and we solve the equation for the phi. So phi is equals to 0 to 2 pi, 0 to pi eta, so upon n I0 L upon lambda square sin square theta R square 1 minus J upon KR cube R square sin theta. So now when we solve the first, phi is equals to 0 to 2 pi, so we get the 2 pi and remaining portion, that means eta upon 8 I0 L upon lambda square 1 minus J upon KR cube is the common, and in the integration term 0 to pi sin cube theta. So we can solve the sin cube theta integration, and so we have directly written for the when we solve this equation, that means the sin cube theta d theta 0 to pi, so we get the value is the 4 by 3. So I have write directly the 4 by 3. We can get this using the trigonometric and the integration equation. So we get the power P is equals to eta pi by 3 I0 L square upon lambda 1 minus J upon KR cube. So this is the value for the power P. This power consists of the real part and imaginary part. When we talk about the power radiate, it is the real power. So as the antenna radiates this real power through the radiation resistance, the radiated power is given by real part of the P. So we can write the P radiate is equals to eta pi by cube I0 L upon lambda pi square. This is the power radiated equation or the radiation power equation. Now radiation resistance. In the terms of the radiation resistance RR and current I0, the power radiate is write as a power radiate equals to 1 by 2 I square R. So I0 square into R, and the resistance is the radiation resistance. So that's why we have write the RR. Equating to expression of R radiate, we get 1 by 2. That means here we put the value of the power radiate. So we write the 1 by 2 I0 square RR is equals to eta pi by cube I0 L upon lambda. So we get RR is equals to eta pi by cube L upon lambda square. This is the radiation resistance. Now we know that the eta is equals to 125. So for the free space, the eta value is the 125. So when we substitute the value of the eta in the RR equation, so we get the RR is equals to 80 pi square L by lambda square. So this is the radiation resistance equation for the oscillating dipole or infinitesimal dipole. Now the directivity for the oscillating dipole. Directivity is obtained by using D0 is equal to 4 pi U max upon P radiate. We know that the relation between the directivity and the U max and the power radiate in the second chapter. This is in the parameter chapter. So U max is the maximum radiation intensity and the P radiate is nothing but the power radiated. So to obtain the directivity, first we have to find out the U max, that means the maximum intensity. The average Poynting vector is given by W average is equal to 1 by 2 real portion E cross H. So 1 by 2 we have the E cross H. This is we consider the E theta A theta into H pi A pi. And the relation between the eta, E theta and H pi, we can write this E theta A theta into E theta upon eta upon A pi. So W average become the 1 by 2 eta E theta square AR. So this is nothing but a W average into AR, where W average is also 1 by 2 n E theta square. And W average become eta by 2 k I0L 4 pi square sin square theta upon R square. So we have given this equation number 1. The radiation intensity U is related with the W average. So we can write this equation as U is equals to R square into W average is equals to n by 2 k I0L upon lambda sin square theta. The maximum value of U is obtained when theta is equals to pi by 2. So we substitute pi by 2 in this equation instead of theta. So we get U max is equals to eta by 2 k I0L upon 4 pi square. So this is the equation for the maximum intensity, U maximum. Same as we have to find the radiation power. So the power radiated by the infinitesimal dipole, we have equation P radiate is equals to eta pi by 3 I0L upon lambda square. So we have the equation for the power radiate and the maximum intensity U maximum. So now we substitute this value, that means the power radiate and U maximum in the directivity equation. So we get that means here we have write the value for the U maximum and for the power radiation that we have write. Using the k is equals to 2 pi by lambda, we get D0 is equals to 3 by 2. The maximum effective aperture is AEM is equals to lambda square upon 4 pi into D0. So we get the maximum effective aperture for the oscillating dipole is 3 lambda square upon 8 pi. So the directivity for the oscillating dipole or infinitesimal dipole is the 3 by 2. And the effective aperture for the oscillating dipole is the 3 lambda square upon 8 pi. So this is the directivity. So here we complete this oscillating dipole analysis. Now in the next chapter we discuss the second one type of the dipole antenna. Thank you. Hello and welcome to our channel Electronics and Communication Engineering. Congratulations to find us for learning. You are watching a lecture series on antenna and propagation that has approx 44 sessions and more are coming up. We have more than 1200 sessions in various lecture series on courses for electronics and communication engineering. Watch it and learn. If you like it, share it, subscribe it and press bell icon to receive all updates on new session. Enjoy learning.